Hi everyone, welcome to Lesson 32. Lesson 32 was our last lesson in Unit 8, so we're getting ready for our second quiz and finally our unit test. Lesson 32 is going to take what we've talked about regarding imaginary numbers, complex numbers, and we're going to link it to roots of quadratics and other polynomials. And we're going to talk about what it means for a quadratic or a polynomial to have imaginary roots. So let's jump right in. Question type 78. Switch my pen here. The instruction is write the expressions below in standard form. So remember, standard form, we've dealt with this before. Standard form of a polynomial is where you have decreasing powers of x. So like ax squared plus bx plus c would be the standard form of a quadratic polynomial. So that's what we want to do. We have a couple of polynomials here that are shown in factored form, right, where it's broken up in individual factors. And we're going to put that in expanded form or standard form. So the process we're doing, so the mechanics are very much like we've seen actually in lesson 31, where we're going to essentially just FOIL this out and then do any simplification we can, and the result would be the standard form of the expanded form or the expanded form of the polynomial. So work on this one with me. We're going to do our first, outer, inner, last. So our first is x times x, so that's going to be x squared. And then our outer is x times 6i, so it's going to be, we could call that 6ix, and it's positive, so we're going to add that. Then we've got our inner inside is negative 6i times x, so we'll call that minus 6ix. Or 6xi. At this point, you can kind of write this however it makes most sense to you. Then we'll talk about the standard form when we put it all together. And now finally we have our last terms, which is negative 6i times positive 6i. Well, that's going to be a negative times a positive is a negative. 6 times 6 is 36. And then I times I is I squared. Now we apply some simplification. X squared pretty much stays where it is for now. This looks pretty easy. We have a plus 6ix and a negative 6ix, so we know those are going to cancel out. And then we have a minus 36i squared. So as a carryover from lesson 31, if you remember, I squared is always equal to negative 1. So we imagine replacing that I squared with a negative 1. I think I said negative 31. Negative 1. So this would be x squared minus 36 times negative 1. Right, because that's what we replace the I squared with, is negative 1. And so 36 times negative 1 is negative 36. And so we have x squared minus negative 36, which simplifies into x squared plus 36. And then that's it. That's the simplest form of this quadratic that we can make. So that's the quadratic in standard form. Let me redo that a little bit. So the roots were x minus 6i and x plus 6i. And those are the roots of the quadratic x squared plus 36, because the quadratic x squared plus 36 does not have any real roots. Okay, hopefully you feel okay about that one. Let's do one more that's similar, and then we'll move on to the other two question types. So there's a couple we're getting through today. Same idea here. Here's another example. We're given the factored form of a polynomial. This is a quadratic because we have our highest power of x will definitely be 2. And just like we did before, we're going to FOIL this out. So first, outer, inner, last. Again, our first terms would be x times x, which is x squared. And then our outer terms will be x times 4i. So that's going to be plus 4ix. And then our inner terms would be x times negative 4i, or negative 4 times x, negative 4i times x. So minus 4ix. And then the last terms will be negative 4i times positive 4i, which is going to be negative 16i squared. Okay, and you're seeing this now. I'm sure you're seeing the pattern at this point. Definitely these middle terms are going to cancel out. That's nice. So this is going to simplify to x squared and then minus 16 times negative 1. Because like we've said before, this I squared term, I squared equals negative 1. Whoops, not t. I squared equals negative 1 because I is the square root of negative 1. So anytime when we're solving these problems, you see an I squared term pop up, we know we can replace that with negative 1. So this becomes x squared minus negative 16, excuse me, because 16 times negative 1 is negative 16, which simplifies into x squared plus 16. And so that's the standard or expanded form of, excuse me again, guys, this polynomial. This is the factored form of the polynomial up here, and the standard form is x squared plus 16. So if you can imagine, just to kind of close this point out, if you can imagine the graph of x squared plus 16. So here's x, here's y. Okay, y equals x squared is a parabola, right? Y equals x squared plus 16. Well, that's going to kind of go up here like this, right? It's going to be transferred up by a value of 16. And so you're going to see that it never crosses the x-axis, right? So it doesn't have any real roots. It only has imaginary roots. Okay. Hopefully no questions there. Let's move on to question type 79. Okay. So 79, let me stay zoomed out here and then we'll zoom in. What is the standard form of a cubic function? So remember what a cubic means. Cubic means it's going to have a degree 3 with rational coefficients, given that the function has known roots of -1 and 4i. And it says assume a leading coefficient of 1, right? So why we have to know that leading coefficient is if you're starting with roots and you're building out a polynomial, then you have to imagine that your polynomial is going to be y or f of x is equal to some leading coefficient a times whatever factors you have, right? And you get your factors from your roots. And there's always going to be this leading coefficient a. If we're given in the problem that a is equal to 1, then we can just essentially drop a because it equals 1 and use our factors to come up with our polynomial. So that's why it's important to know that what the leading coefficient is, because just with the roots by itself, you can have an infinite number of different polynomials. So you need to know what the leading coefficient is so you can consider that. Anyway, let's see what we're given here. We have known roots of -1. So let's see, I'm going to write out here, we've got roots. One of the roots is -1. And then one of the roots is 4i. Okay. But we're told that this is a cubic function, which means it's going to have 3 roots, right? And we're only given 2. So the question then immediately becomes, well, what's the third root? Because only when we have the third root can we come up with the 3 factors. Well, if you remember when we talked about irrational roots, we said that there was a conjugate root theorem, right? Which meant that, say, for example, if the square root of 3 is a root, then negative square root of 3 would also be a root. That the conjugate of an irrational number is itself a root if the irrational number is a root, especially if you're dealing with rational coefficients. So the same thing applies to imaginary numbers. Let's switch back to blue here. So we know that 4i is a root, right? So conjugate root theorem applied to imaginary or complex numbers means that -4i is also a root, right? Because if one complex or imaginary number is present, then its conjugate must also be present. That's going to come up a lot with this type of question. So that then gives us our 3 roots, right? We knew we were dealing with a cubic, so we knew we had to have 3 roots. That's how we're going to get the third one. We're starting with what we know, right? And then we apply that conjugate root theorem to that imaginary number to get the third root. So once we have the roots, right, we can come up with the factors, and hopefully you guys are getting pretty, fast, getting familiar with this. Where we start with roots. Remember, these are roots over here, which are already labeled, and then we go to the factors, and the factor is always x minus the root, right? So it's for instance, if we have a root of -1, then the factor is x minus -1, or that simplifies into x plus 1. Right? Remember, this would be the root this would be the factor that's associated with that root. Okay? Then we do the same thing down here. If we have a root of 4i, then the factor must be x minus 4i. Okay, it's x minus the root. The factor is x minus the root. Down here, if we have a root of negative 4i, then the factor must be x plus 4i. So these must be our 3 factors of our cubic polynomial. Okay, we need to put this though in standard form. So it's good that we know the factors, right? We have a leading coefficient of 1. So that tells us that what this polynomial is y is equal to some leading coefficient a, which we know that, times our factors, x minus 4i. I'm going to do these two first, and you'll see in a reason why. X plus 4i, and then x plus 1. So those are our factors. Now that would, oh, actually, let me apply now the leading coefficient. We told to have a leading coefficient of 1, so that means we can replace this a with a 1. Okay, and then this then simplifies into y is equal to x minus 4i times x plus 4i, fix that plus, times x plus 1. Now this would be our answer if we were tasked with just coming up with a factored form of this polynomial, but unfortunately we're not. We're actually told to figure out the standard form. So we've actually got to multiply this out, right? We got to FOIL everything out. Probably the best way to do that is to pick two of them, right? We know we got to kind of FOIL these three terms all together here, these three factors. The best way to do that is to just pick two, do those first, and then if you get a binomial as a result, which we probably would with these two conjugates, then we can multiply that binomial with the third factor, which is this one. That'll make more sense if we actually do it, so let's try that. So what we're going to do is we're actually going to multiply these first two first. We're going to apply FOIL. So first, outer, inner, last times those, just the first two factors. So this is going to give us y is equal to, multiplying our first, x times x is x squared. Then our outer, x times 4i is plus 4ix. Then our inner, which would be minus 4ix. And then our last, which would be minus 16i squared. Okay, and all this is still multiplied times x plus 1, or by x plus 1, because we still have this third factor here waiting for us to do something with that here in a second. Okay, some quick things going on here. We see that these terms cancel. We have a plus 4ix and a negative 4ix. And remember always what happens with I squared. I squared becomes negative 1. So this simplifies into y is equal to x squared. Was x squared minus 16i squared once these two middle terms canceled out. But since it's minus 16i squared is negative 1, so it becomes minus negative 16, or x squared plus 16. Right, that simplifies. And then we've still got this last term over here, this factor we haven't done anything yet with, which is the x plus 1. Okay, so good. So now we've simplified this down. You know, we've taken these two factors, multiplied them together, and gotten a new binomial, x squared plus 16. So now we have x squared plus 16 times x plus 1. We're still not there yet, right? Because we need to get this thing into a standard form, and we're still sitting in a factored form. So now we're going to apply FOIL again. Right, we're going to do first, outer, inner, last. Okay, so this is going to be y is equal to, our first would be x squared times x, so that's going to be x cubed. Outer would be x squared times 1, so that's going to be plus x squared. Inner is going to be, let's see, inner is going to be 16x. And then last is going to be 16 times 1, which is 16. And in looking at it right away, we can see, well, there's no more simplification we can do here, right? There's no like terms we can combine or anything. So actually, that's our answer. So y is equal to x cubed plus x squared plus 16x plus 16. So this cubic polynomial would have the roots negative 1 and 4i, and must therefore also have negative 4i and a leading coefficient of 1. So hopefully that one wasn't too bad. That was question type 79. Let's do one more question type. I know this video is running long, but thanks for dealing with me on this one. This is question type 80. And question type 80 has to do with combining imaginary and irrational roots, so this is going to be fun. This is question is asking, what is the factored form of a function with rational coefficients given that the function has known roots of all these guys right here? So there's at least 4 known roots, and there might be some more. Assume we have a leading coefficient of 1. Okay, Here's what we like about this problem. It's asking us what is the factored form. Factored form means we don't have to expand it out. We don't have to get standard form. We're good with factored form, which means if we can find the factors associated with these roots and any other roots that it might have, then we're good. Okay, we can start by listing our roots out, kind of like we did before. So here's our roots. We have 0, we have 2, we have square root of 3, and then I'm going to skip a line down and say negative 3i. I'm sorry, negative 7i. Okay, and here's why. We see that we have an irrational root, right? Square root of 3 is an irrational number, and just remember what an irrational number is. We know that there's a conjugate root theorem that applies to irrational numbers, which means if an irrational number is a root for a coefficient that has a polynomial that has rational coefficients. If an irrational number is a root, then that irrational number's conjugate must also be a root. So that means if we know that square root of 3 is a root, then we also know that negative square root of 3 must also be a root, because these come in conjugate pairs according to the conjugate root theorem. Okay, that applies to irrational numbers. That goes back to the beginning of lesson 8. We also know that conjugate root theorem applies to imaginary numbers as well, so negative 7i. So we know that if negative 7i is a root, well then 7i itself, which is the conjugate of negative 7i, must also be a root. So here we have a whopping 6 roots here, so we know we're dealing with a degree 6 polynomial. Fortunately, like we said, we only have to go to factored form, so this isn't terrible to work with. We know that to get from the roots to our polynomial, well, the first thing we need to do is find our factors, right? So we're going to do that kind of one by one for each root. Remember, the factors are x minus whatever the root is. Well, in the case of if the root is 0 itself, then the factor is x minus 0, which is just x. So x by itself is a factor of this polynomial because 0 is one of the roots. All right, let's look at the next root. The next root is the number 2. So the factor is x minus the root. So that's going to be x minus 2. All right, keep on going down from there. We know that square root of 3 is a root. So x minus square root of 3, which is x minus the root, must be a factor. Okay. Negative square root of 3 is a root. So our factor is x minus negative square root of 3, which simplifies into x plus square root of 3. Okay. And then the hits just keep on coming. Negative 7i is a root, so the factor must be x minus negative 7i, which simplifies into x plus 7i. And then 7i is a root, so a factor must be x minus the root, which means x minus 7i. Okay, so here's all 6 of our roots, our factors. I'm getting my words mixed up. All 6 of our factors, and since we're excuse me, since we're tasked with coming up with the factored form of the polynomial, what we said before is if you know the roots of a polynomial, and therefore if you know the factors of a polynomial, then you can build the polynomial itself by saying y is equal to, or f of x is equal to some leading coefficient a times all of your factors, right? Now often we don't know what the leading coefficient is, except we're given it in this problem. We're told we have a leading coefficient of 1. So that gets pretty easy. So then this factored form of this polynomial is y is equal to a, which is 1 in this case, times all of these factors, x times x minus 2 times x minus square root of 3 times x plus square root of 3 times x plus 7i times x minus 7i. Whew, that was a good one. So 6 factors, a big polynomial. Fortunately, the instructions just said what is the factored form, so we can stop there. We don't have to try to multiply all this out because we'd be here a week trying to do this. And that's our answer. So that's the last question type. Try the practice quiz, guys. I will post my answers in Google Classroom so you see how you're doing. Continue working on the Delta Math. When I see you again, we will take any questions, we'll do some practice, and we'll get ready to wrap up Unit 8. Okay, thank you very much, guys. Have a good day, and I will talk to you soon.